Damping. Well, what's damping? Damping is basically a resistance to motion. Okay? And that resistance, we're going to just be talking about viscous damping, which is a resistance to motion, okay, and it's proportional to the velocity of that motion. If the system is not moving, there's no damping force. Okay? So like you pull back a spring and a damper, and you hold it there, okay, the damper does nothing. Okay, but the spring force is trying to return it. You let go, obviously you start getting motion, okay? So the spring is going to force it back, but the damper is always opposing that motion proportional to how fast the thing's going. Okay, that's what a damper does. A damper in your car, shock absorber, is exactly the same thing. If you had no shock absorber in your car and you hit a bump, the car would oscillate forever, okay? It would just keep going up and down because you've excited it, okay? Whereas the damper will take out that energy, okay, by using, like I said, and that energy that's taken out is proportional to how fast the thing is moving, okay? Viscous damping is what it's called. So the force opposing the motion, this is really important. The same with springs. Spring force and damping force will always oppose motion, okay? It will be opposite to the way the thing wants to move, okay? So the damping force is C, which is our damping constant, okay? And that's a characteristic of the damper, times by the relative velocity of x and y, okay? X dot minus y dot. So that's, it could be shown as a real damper. Often this bit up here, you'll have some sort of orifice through the piston, okay? So fluid can go from one side to the other, okay? And we all know that orifices, back in level 1 fluids, that will cause some sort of that's a restriction, and that restriction will control how quickly that damper can move, how quickly that piston can move through the fluid, okay, which is obviously causing you damping. That's just a schematic of how dampers are drawn, okay, and so you'll see that quite frequently.